Welcome to the Martz-Kohl Observatory, everybody online and everybody here. We're here to welcome a very special guest speaker tonight, Dan Krysak. Dan is actually a New Yorker originally, and he grew up in New York State and attended SUNY Potsdam with degrees in speech communication and archaeology. Then he went on to get a master's degree in a subject that I don't think many people see in graduate school or anyplace else. Planetary volcanology. I can't wait to hear more about that, Dan. That's an amazing field. Dan started working at his current company, Malin Space Science Systems, in San Diego, California. It's a private California-based technology company that designs and operates equipment for unmanned spacecraft. And his work has included, Dan allowed me to call him a Martian. It included operating the cameras on the Mars rovers and the Juno mission that was launched to Jupiter. And interestingly enough, it's almost exactly 20 years ago, just about a week and a half ago. A good anniversary. Happy anniversary, Dan. That's a very important project. So a couple of other announcements that I want to make tonight too. I've already mentioned it to some of the folks here, but our speaker who was here last month, one of our speakers, Carl Hergenrother, had discovered many, I believe dozens of asteroids and comets throughout the solar system. And one of the questions that came up in our QA period was somebody wanted to know if they thought we, with our own equipment, could discover an asteroid from here. And he said, certainly it shouldn't be too hard. Most of the big ones have been discovered, but he said, you know, he has many that he has discovered. They're numbered, but not named. So he very kindly offered to donate one of his recently discovered asteroids to us and name it the Martz-Kohl asteroid.
All right.
And that's very exciting. I spoke to Ron Cole earlier today and told him about it. Told him his name might be on an asteroid, and he said, well, maybe that's going to be one of the ones that hits Earth. In which case I said, as a dentist, he'd like that because he'd have at least one more big cavity to fill. But I thought that was very exciting. Having polled all the board members, I think everybody agrees that we probably want to accept that invitation. And we'll stay in touch with Carl. And hopefully that between us, we can find one of the asteroids that's visible from here that we can photograph, and we know where our name is placed. So that's really good news. And Dan, since you're operating on Mars, if you happen to see something that you can name Martz-Kohl when you're around Mars, we'd be delighted with that too. But that's a different subject. So if you'd like to take it from here, the podium is yours, sir.
All righty. Well, thank you all very much for having me. As we said, my name is Daniel. I work for Malin Space Science Systems out here in San Diego. I'll give you a little background on the company. We are a private company. I've been around for, strangely enough, going on 30 years now. It's a scary thought. Yeah, we specialize in building space cameras. We have cameras really throughout the solar system. We've got quite a number at Mars. Have a number of cameras on the Curiosity rover that we'll be talking about tonight. We have some cameras on the Perseverance rover that landed just earlier this year in February. We have some cameras around a couple orbiters that are on Mars as well right now. We got another camera on the Juno spacecraft at Jupiter, which we'll also talk about tonight. And then lastly, another one on the Lunar Reconnaissance Orbiter around the moon. So we're kind of all over the solar system. Give you a background about myself. I've been working here now for about 9.5 years. I started back in early 2012. I hired in specifically to work on the Curiosity rover. It was about 6 months before we landed on Mars. Since then, I've also added Dune Juno, as we said. So we'll definitely be focusing on those two missions tonight. A little bit more background about myself. As we said, I'm a New York State native. I'm from Binghamton originally. And did my master's degree at University of Buffalo in planetary volcanology. Kind of fun little complete the circle, I mapped out the geologic history of a volcano on Mars. And at the time I was doing it, I was using images from an instrument called CTX. That was part of the part of the Mars Reconnaissance Orbiter, and did that for a couple of years. And right towards the end of my degree, my advisor had told me about this company in San Diego, and they were, looking to hire some people to work on the Curiosity rover at that point. And lo and behold, as I'm looking around, it's like, oh, the CTX camera is actually built by this company. So I got the job about a year later, and yeah, so the camera that I used to do my master's degree is, was built by the company I'm at now. So it was a fun complete the circle for me. So without further ado, I got some slides here. I'll share my screen and we'll go into that. Start the presentation here. So as we said, we'll be talking about both the Mars Curiosity rover and the Juno mission tonight. So we'll start with MSL. Particularly on MSL, we have 4 cameras that we built. There's 2 mast cams. They're mounted on the mast. Those are 134 millimeter cameras. We have another camera on the end of the arm called MOLLE. It stands for the Mars Hand Lens Imager. I'll go into the details of that in a little bit. And then lastly, we have another camera named Marty. And this one's kind of placed interestingly. It's mounted on the undercarriage of the rover and actually pointed straight down. So the reasoning for that, we'll start with Marty here and go into the details on that. The reason for that was when the Curiosity rover was going to land on Mars, we had to have a different landing system for it than we did with the MER rover, Spirit and Opportunity, as well as Sojourner Pathfinder rover. In the mid-90s. Those rovers were much smaller, and they used the airbag system to land, where they came through the atmosphere, the airbags inflated around them, and they kind of just bounced around on the surface of Mars until they came to rest. The Curiosity rover was much larger than that. The rover itself is about the size of a car and much heavier as well. So the airbag system just wasn't going to work. They would have just popped as soon as they hit the ground. So the engineers at JPL developed the new system called the Sky Crane system. And it's quite literally ultimately a platform with retro rockets on the sides, and the rover's mounted underneath it, and it's lowered down on a winch to get to the surface. So it's a very ingenious and very daring system, and Curiosity was going to be the first rover that was going to use it. So the idea of the Marty camera was, when the capsule containing the rover was going through the atmosphere, going to land on Mars, there's a point during its descent where it's tens of kilometers up off the ground still. The heat shield would come off on the bottom, and at that point, with this new landing system, the rover is completely exposed to the Martian atmosphere at that point. So the idea was we would have this camera mounted on the undercarriage, pointed straight down at the surface of Mars, so that when the heat shield came off, we'd be able to just basically film a video of our descent all the way from the upper atmosphere until we landed on the ground. So this image you're looking at right here, this is just one frame of that entire descent video. I won't show the video just for the sake of time. It's a number of minutes long, 3-4 minutes long, but you could see all sorts of YouTube videos made. People have put their own videos together. They're very impressive. This right here is one of the earlier frames. This thing in the center, this is actually the heat shield itself as it just separated from the base of the capsule. And basically the heat shield would just go and land on the ground wherever it does. And so again, we're still tens of kilometers up here off the atmosphere. And we saw some pretty interesting things. You can see this dark area right here. This is a bunch of dark sand dunes that are within the crater that we landed in. The crater is named Gale Crater. You could see some other, smaller craters kind of throughout here. Very interesting terrain here. And so the Marty video actually proved to be, there are really a number of reasons for it. A lot of the engineers, since they're using this new Sky Crane system, one of the things they wanted to do is just really get a visual look at what this was going to be like. You could read all the telemetry you want, look at numbers and things like that, but getting a visual representation of everything was very important. And so when we watched the video in the end, it was great to see. One of the things the engineers were wondering about was whether or not we were actually going to start kind of rotating around, spinning around as we were going down, and the wind would start blowing us around, and they weren't really sure how much that would affect things or not. And in the end, when you watch the video, we really didn't spin around or blow around in the wind much at all. So it was actually really, really interesting to get to see that and just get that visual kind of sense of just seeing what it was like. So worked out great for the engineers, and worked out great really for the outreach side of things too as well. So definitely recommend checking out the video on YouTube if you can. Now, that being said, you're thinking, okay, well, we landed on the ground. Now the camera's only, 2 feet off the ground. Do you really get to use it for anything now? And we really do. There's a lot of things that we've been able to use it for. Move along. This is an image we took a number of years ago at this point, back in 2017. One of the things we've used it for before are what's called change detection. So you can see this image right here. This is just a day later, a day between the two images, January 23rd and 24th. And you can see this is right here in the top left. That's the rover's wheel itself. And this is just the tracks of the rover as it drove through this little bit of dust right here in sand. And you can see some other ripples in here. And just in one day, you could see how much the wind blew and actually changed the surface that much. So even though, this camera is made for really, one specific purpose right in the very beginning of the mission, years later, we're still able to use it for lots of cool things, really get to see in this case, the wind that's on Mars. Another thing that we've done before is we've done what are called drive videos. So when we go for a long drive, 30, 40, 50 kilometers, we'll actually turn Marty on and do the same thing, take a video of our drive. And that's kind of interesting because, as we're driving, we'll drive like every foot or so, we'll be able to take an image. And since the distance between those two images, you could actually build what's called a DEM, a digital elevation model, or a DTM, digital terrain model, based entirely on those two images. You could really make the equivalent of stereo images between those two things. So really kind of interesting way that we're able to just use one of our cameras that, again, was really specifically designed for one thing right in the very beginning of the mission. But again, it's a perfectly working camera, works very well. So no reason to not continue to use it. So moving on now, we'll talk about the mass cams. If you'll remember earlier, I mentioned we have two of them. There's the 100 millimeter and the 34 millimeter. And really what that means is really all the cameras on the Curiosity rover, we kind of designed them to be kind of like point and shoot cameras. So you just basically aim the camera, take your image, and then you're good. So with the 34 millimeter camera, what that basically means is think of it kind of like the zoom level, if you will, of the camera. With a 34 millimeter camera, that's very similar to a typical point and shoot camera. Right when you power it on, you're not zooming in the distance or anything. And the 100 millimeter, you could think of taking that same point and shoot camera and then just zooming it really far into the distance. So it lets you be able to see a lot further in the distance. So I'm going to show you two images here. I'll bounce back and forth. This right here that we're looking at is the 34 millimeter camera. And I want you all to focus kind of on the left side of the image here. You can see this rock outcrop that's sticking out right there. I'm going to jump forward. This is the 100 millimeter camera. Both images were taken at the exact same time from the exact same distance, quite literally the exact same second from the same spot on Mars. I'll bounce back and forth. You can see how further in the distance we're able to see with the 100 millimeter than we can with the 34 millimeter. So there's really a number of reasons why we've got the camera set up like that. One really important reason is when you're working with spacecraft that are on another planet that you're never going to see again, you certainly want to mitigate the amount of wear and tear that you place on the spacecraft. Moving parts, any engineer could tell you moving parts, they're great, but since they're moving parts, they will eventually wear out. So you really want to utilize them when you can, but not overutilize them to the point where you wear them out prematurely. So one of the cool things with the mass cam is we could do these 34 millimeter images, get a lot of context for what we're seeing in the area, and then we do the 100 millimeter image right after it, and we could see again that much further in the distance and say, okay, now we could see much more detail of this particular rock outcrop right there. Is this something that we want to drive up to? Is this something that's very scientifically interesting, something that we want to look at? And we're able to do that without actually having to physically drive up to it. We can make our decisions based, right here, based on this image, for example, and then decide if it is interesting, then we could drive up to it, and add some more wear and tear to the vehicle, if you will, because we do find it interesting. So it's just, once again, one of the many different things we could do with it in a very a good way of just trying to utilize what we have to help mitigate extra wear and tear on the spacecraft itself. So with that being said, we could certainly do more than just, take, two depth of field images like this. Another thing we could do with mass cam is we could actually look up pretty close to the surface of what's in front of us. So this image right here is looking at a small little outcrop right in front of the rover itself, just a matter of feet in front of the rover. And there's a couple things I'm going to want you to notice about this image. First, with a camera that could see far into the distance, even the 34 millimeter, you could see that even a few feet in front of the rover, we're able to really zoom in and get a lot of high detail there. So the camera is very versatile in that aspect. Another thing to notice, if you look kind of the top and the bottom here, you'll see kind of like these jagged edges right here. Now, this is not just a single image. This is actually 6 separate images put together. So the idea behind that is our images are about 1600 by 1200 pixels tall, so about the size of an average computer display. Nothing big like a 2 or 4K, but a pretty average computer display. And what we do is, instead of having a gigantic resolution CCD on one of our cameras, which would be very expensive, plus something you really need to test, we could do a smaller sensor on the camera. Lets us get quote unquote smaller images, but we could take a series of them all together and then stitch them together and make this nice seamless image. We call these stitched together images mosaics. So as a result of these 1600 pixel wide images, you can now all of a sudden make a 3600 or 45 or really as big of an image as you want, just by stitching them together. And then making this nice seamless image. So again, this is another way that we're able to utilize the hardware that we have and really make a really, really impressive product out of it that the science team members could use, that even the engineers could use for various things. So, and this is certainly a common thing that we do here. We'll take what we call workspace images, these big mosaics of right in front of the rover, so we could get a high resolution detail of what's there. And then we could decide if we want to take the arm out and start using some of the instrumentation on the end of the arm at this thing that's only a few feet in front of us. So one of the really fun things with mass cams, and really, I mean, any space exploration, is finding the things that you had no idea where you're going to come across. So this is another mass cam image. This was, we took some contextual imaging, some mosaics, and somebody noticed this kind of darker object kind of off in the distance, one of the images. And as a result, we thought, oh, that's pretty interesting. So we drove up closer to it. Turns out this is actually a meteorite that we found on the ground. I believe, I don't remember for sure. I think this one is maybe the size of a tennis ball, not very large, but none of us expected it to be there. We just found this meteorite right there laying on the ground. So we drove up to it, took some images of it, performed some science on it. If not sure if it shows up through the video chat here, but you could see these there's a couple dots on it, whiter colored dots. That was actually one of the instruments on board the rover is a laser imager, if you will, and they actually lasered the rocks. That's what those dots are right there, where their laser had hit it, to get some spectroscopy science on this meteorite. So something none of us expected to see, but it happened to be right there in one of the images one day. It's like, that's awesome. We have to go up to that and look at it. So really pretty interesting. And again, something that we saw in the mass cams, just because we had a mosaic of a particular area there, and just we were looking at the contextual image, and we just happened to see this one thing in it right there. So really, really pretty interesting. So with that being said, going further on with some of the cool things we're able to do with the mass cams. So now this is another mosaic, if you will. You could see these kind of 2 long rectangles. These are really actually 2 separate mosaics put together. You could kind of see a little bit of a slight jagged edge right there in the top and a little bit kind of on the sides here. So there's actually 4 separate tiers worth, 4 separate tiers, 4 separate rows worth of images that we're able to stitch together. Now, these are really interesting because this allows us to be able to set our focus for, each tier like that, each image individually. So even though we've got an image that's got rocks that are up really close up front here, and then, stuff that's further mid-ground distance and then way in the back there, since we're doing these all with this mosaic, we're able to set the focus differently for each one and make sure that we're able to get all these images perfectly in focus, no matter how close it is or how far away it is. So we're able to do that in just this one single image. So I like showing this one a lot because it's a good example of, we got the stuff really up close here, and then you get really further away into the distance. Kind of hard to see probably on the screen sharing, but really far in the distance. We're able to get, like I said, everything very well in focus, as well as all the stuff in the middle ground too. So So you can see a lot of detail. You can see lots of outcrops, kind of pointing out right there. There are, some dark sand dunes in there. So lots of very interesting detail just in these couple mosaics that we're able to put together. And then lastly, one of the really fun things we're able to do is we take what are called, every now and then we take what are called 360-degree panoramas. So this image right here, if you took the left side, would actually match up with what's right there on the right side. So if you stitch the two together kind of in a circle and sat in the middle, this is what you would see with the rover. So you could see there's some, rover hardware there. These are the wheels themselves. This is actually kind of cool. You could see the arm itself. We actually had the arm out when this image is being, or when these images were being taken. You could even see the mountain in the background. This mountain's name is Mount Sharp. It's in the very center of the crater that we landed in. And again, this one, you could kind of see those jagged edges again. I forget how many images make up this one, but there's got to be, I think, at least 7 or 8 tiers worth of images to get all the way into the background. And again, because since we're able to set the focus for each individual image like that, we're able to get, perfect clarity and focus throughout the entire panoramic image like that. So we do these from time to time, certainly when we get to a newer area, really nice to be able to get just that big contextual images all around us like that. And I always think it's kind of fun when you get some of the hardware in there too. So you get to see the rover itself. Typically, we don't take a lot of pictures of the hardware. This kind of area right there, it's all blacked out. Those are just images we didn't take of the rover itself because, we don't want to, continuously take images of the rover deck. We know that the rover is never going to be changing. There's no science to be performed on that. So it just saves us images, saves us data volume on board our onboard storage for all the cameras. So you really do need to kind of be smart with the way you're utilizing your own instruments, certainly, just like we do with how much we want to put wear and tear on the rover itself. So finally, I like to always end my mass cam discussion with this little 4-frame image. This is actually a Martian sunset. So this is the edge of the crater rim that we landed in. And this is our sun going down on the surface of Mars. This is what it would look like if you were standing there watching the sun go down. So it's a really nice way just to end a nice little chat about mass cam itself. I always like shown that one. The cameras, again, are very versatile. In addition to the daylight images, we could certainly do darker, dusk time images and even night times as well. So let's move on to the Molly camera now. This is the camera that I said was mounted on the end of the arm and stands for the Mars Hand Lens Imager. Now, as geologists, one of the tools that we have within our toolkit are hand lenses, just like a jeweler would use for looking at jewelry up close. Geologists will use the exact same thing. If you've got a small rock with maybe really small crystalline or grain structure like that, you could use the hand lens just to see up close to it and get a magnified view of what you're looking at. So Molly is quite literally the same thing. We're able to get the Molly instrument about 2 centimeters up to the face of a rock, technically a little bit closer, and we're able to zoom in very close to it. You could see, again, the grain structure, some of the rocks, give you all an idea for scale on this one. You can see right here, there's some pebbles, and then even up right there, there's some actual sand grains. So we could get really close to the rock. I'm going to guess this little rock we're seeing right here is probably a couple centimeters wide, I'd say. I'm not entirely sure, but we could get very close, as I said, about 2 centimeters. And again, same thing, we're able to set the focus of our images very well, just like with the mass cams, and get everything perfect clarity for all the images like that. So with that being said, if we're able to get that close to a rock, you might be thinking to yourself, it's like, okay, well, that's good. But if you get so close, you might be, blocking any sort of light from getting in there. You might not be able to see a lot of what you're looking at on the rock face. So one of the things we did to mitigate that was to install some LEDs on the face of Molly. So we could use them just like a flash, just like you would on a camera. Now this image we're looking at, this is actually a mass cam image that we took in the middle of the night. And you can see right here, kind of in the upper right, this is a part of the arm itself, the arm turret with Molly on the end of it. And it's looking at one of our drill holes from earlier on in the mission. And this has got its white LEDs turned on. And now, certainly on Mars, there's no light pollution. So you could see with just those few LEDs turned on, how well the surface is illuminated. We know this is a completely pitch black, dark environment, but those LEDs illuminate everything very well as if it was daylight. So we're able to see extremely well no matter what distance we are from the rock, and be able to illuminate the surface for anything we need to do. So here is an actual MOLLE image itself, and a different one that we took in the middle of the night with the LEDs on. This one's actually kind of interesting because this rock we had driven over, and we accidentally broke off part of the rock right there. And it was pretty cool. We thought, oh, that's really interesting. Might as well, if we broke open the insides of this rock, let's get some up close images of this and see what the crystalline structure, grain structure looks like here. And so now you'll notice here, there's definitely kind of a brighter whitish part on the rock itself. Now, one of the other kind of tools that geologists always have in their toolkits are actually black lights, ultraviolet lights. That will tell you, or rather, I should say, some minerals, some rocks will fluoresce under a black light, and that will tell you, or that'll at least guide you into figuring out what the composition of a particular rock is, whether or not it fluoresces under black light. So, with that being said, we did the same thing on MOLLE. We have two ultraviolet LEDs mounted right next to those white LEDs, and this is a perfect example. I'll flip back and forth between the two images. So we got the white LEDs going to ultraviolet, and we figured, well, if we've got a really bright area in that rock, let's see if that fluoresces under the black light. Whether it does or does not is not a bad thing. That'll just help us decide or help us determine what the composition of this rock is. Now, in the end, this one did not fluoresce, which again is not a bad thing. It just helped the science team members decide what that was. And I got to be completely honest with you, this was, I think, 7 or 8 years ago, and I do not remember what the composition of this rock was anymore. But still really interesting nonetheless to be able to get to see both images like that illuminated in the exact same scene with the two different lights turned on. So lastly, for MOLLE, as I'm sure many of you have seen, one of the really cool things that we developed for was the ability for Curiosity to be able to quite literally take a selfie. The rover does it the exact same way that we would here on Earth. She literally holds the arm out, turns the MOLLE camera back on her, and takes the image. Now, with that being said, keen-eye observers will probably notice there is no arm right in the image itself right here. It's like, well, how's that possible? Whenever you take a selfie, you always see your arm sticking out from underneath the camera. So this image is a little bit misleading because it's not one single image. This is actually a mosaic, just like the mass cams. I think this one's got to be 50 or 60 different images. So we've got an image right here in the top left, and then one next to it, and you keep on going down. Same with the mass cams. You do all your different tiers of images, and by the time you get about the halfway point, right where the arm itself would be in the field of view of the camera, we're able to flip the arm up 180 degrees so that the elbow joint, if you will, is now pointed up above the camera out of the field of view, and then continue taking our tiers as we go down all the way to the bottom. And then from there, since we know exactly where the arm will be during this whole sequence of events, we're able to easily stitch out or easily remove the arm as we stitch all the images together and make a very seamless image. If you look at this image full scale, you definitely can see a little bit of seaming on there. Kind of hard to see at the zoom level we're at right now, but I believe this image is 20 or 30,000 pixels wide, very large. It definitely would fill up an entire wall if you had it on just one computer screen. So very, very large image in the end. But again, same idea with those mosaics with Mastcam. We're able to nicely, seamlessly stitch them all together. So that's really, like, I love ending the MSL talk certainly with the selfies like that. Very nice. I'll jump back really quick. Very nice contextual images of what we're able to do with this camera on Mars. So switching gears, we'll go further out in the solar system now and go look at Jupiter. So as I said, we have the JunoCam instrument that is on the Juno mission at Jupiter. Now, Juno is a very different mission than a lot of the orbiters we've done before. First, we've never had a camera, our company's never had a camera at Jupiter before. A lot of our stuff was always at Mars. So that led obviously to some interesting engineering challenges because of different light levels. You're much further away from the sun. But Juno is a really interesting spacecraft because if you look at it here, it's kind of in this, Y-shaped, Y shape, if you will. But the spacecraft itself is actually rotating on its axis at about 2 RPMs. And JunoCam itself, you can see, is mounted in between these two solar arrays right there, pointed outwards at the planet. So what that means, as the spacecraft is rotating, as it's spinning right there, that means JunoCam itself is only pointed at the planet for a handful of seconds out of that whole spin right there. And that really led to a lot of interesting engineering challenges, because Juno, unlike the Curiosity rover or Perseverance or any of those cameras, Juno is not really a straightforward point and shoot camera, if you will. We don't just point it at the planet, take an image, and then we're done. Since we're moving, we basically utilize the movement of the spacecraft in order to fill in all the lines on our sensor, our CCD on our camera itself. And again, since not only is the spacecraft spinning, but it's also moving as it goes down the planet, that in and of itself, if you're interested in cameras, you'll know that will create blur as you're going along like that. So what we use is what's called TDI, time delayed integration, and it's a weird concept. Took me a little while to understand it, but then once I figured it out, it makes perfect sense. Basically, what you do is for any pixel on your sensor on your camera right there, you basically say after X amount of milliseconds, shift that charge up 1 pixel, so that at that point, the camera, or rather the spacecraft, will have moved and the camera is going to move with it. That 1 pixel itself, as it's shifting the charge up, is always going to be pointed at the same spot on the planet. So that's what allows us to be able to take these nice images of Jupiter without having smear in them like that. Again, it's kind of a strange concept. Definitely, it actually took me a little while. Like I said, it was a number of weeks before I really finally understood how it worked. So kind of an odd concept, but very cool nonetheless. The other really interesting thing about the Juno mission is we are in a polar orbit around Jupiter. Instead of being kind of an equatorial orbit around the planet, well, we decided to put the spacecraft in the polar orbit so we could actually view the poles as we're going around. And the good thing about that is, since we haven't really had a dedicated spacecraft at Jupiter since Galileo, in the 90s and going into the 2000s like that, and that one was really kind of just equatorial and really looking at a lot of the moons. The idea with Juno was we'll finally be able to see the poles, because as well, looking here at Earth, whether you're looking at Jupiter through a telescope in your backyard, or even like the Hubble telescope, you could really only see the equator because all the planets are on the same equatorial plane around the sun. So Juno being around the poles, we'd finally, after all this time, have something there where we could see the poles themselves up close and really get an idea of what's going on. And then in addition to that, Jupiter has an extremely high radiation environment. So we couldn't just do a nice circular orbit around the planet. We're actually in a very highly elliptical orbit going around the planet. It actually takes us up until just earlier this month when we went into the extended mission, it would actually take us 53 and a half days to get from the very equator of the planet all the way out and then back around again. So about 2 months. We're down to, I think it's 47 or 48 right now, where we're at right now with our new orbit. But so it still takes a while. We plan it only about once every month and a half. And again, there's a number of reasons for that, one of which is certainly so we're not continuously bathed in all that radiation. So without further ado, let's start looking at some images from Juno. I've talked enough about it. So one of the really cool things that we were able to do with the camera was when we were on our way in to get to the planet itself, we figured, well, the planet's right in front of us as we're flying into it. Why don't we turn on the camera and start taking some images? So what we decided to do is we would take an image once every 15 minutes and we would make a movie, kind of just like what we did with Marty. We could stitch all those images together. And in this case, what we're going to be able to do is we're going to see Jupiter, and then we're going to see the 4 Galilean satellites around it: Io, Europa, Ganymede, and Callisto. And we're going to be able to see those moons, those satellites orbiting around Jupiter. And I'll play the video here now. The idea behind this is exactly what Galileo saw when he looked through his telescope and saw these little dots kind of, dancing around Jupiter there. And that's what ultimately led him to say, oh, maybe Earth isn't the center of the solar system, center of the universe. It's actually just this one planet orbiting around the sun. The sun's the center of our solar system. And I'll play this again here. And so this is what he would have seen in his telescope all those years ago. So this was kind of just a fun little homage to him as we were coming in. Again, this wasn't really planned initially, but as we're getting closer to Jupiter throughout the years, we said, oh, we've got to do this. The camera could handle it. We could do it just fine. We really should do this. And the video came out great. I'll play it one more time here. You'll notice there are a couple jumps in there where the moons kind of jump. We did have a couple issues actually at the time. But in the end, the video still came out great. Really happy to be part of that one. So, and again, it was a great outreach video for us to show as well. So move forward here. So let's look at some of the actual Juno images themselves. So this right here is actually looking straight down at the North Pole of Jupiter right here. The pole itself is kind of this darker, hopefully it shows up there. It's kind of like this darker bluish area. Right off the bat, I will say the camera itself, we did design really to be more of a public outreach camera. So it's not, the sensor was never color calibrated for us to do any sort of color-based science like that. So the colors you are seeing here are false colors. I did process this image actually just yesterday to kind of make the color stand out there around the pole itself. But yeah, so you can see it's a pretty interesting thing. So Jupiter being a gas planet, whenever you see the images of it, you again see it from the sides and you see all the bands, all the striations as they're moving, laterally across the planet. But when we got to the poles, we weren't really sure what it was going to look like. Obviously, we had some ideas based on Cassini when that was at Saturn. And we just assume very well maybe similar to Cassini, but could be different yet. So in the end, when we got there and we looked at the poles, it's in my opinion, for what I thought it was going to be, it's a much more chaotic environment than I thought. You could see there's all sorts of storms here. Unlike the nice lateral bands and striations throughout the rest of the planet, in the poles, it's all over the place. You've got some anticyclonic storms right there. Some are rotating clockwise, some are counterclockwise. Others are more just kind of a random pattern. The winds are moving all over the place, and it's a very, very interesting environment. It's certainly not what I thought it was going to be, but certainly very interesting nonetheless. So really had no idea what to expect, but finally in human history, we're able to finally see what the planet or what the planet's poles themselves look like. So move on to the next image. So I had mentioned earlier how the spacecraft is spinning, and the camera's only pointed at the spacecraft for a handful of seconds throughout that spin. So this image you're looking at right here, this is actually a raw image that we get down directly from the spacecraft. So again, unlike one of the point and shoot cameras where you take your image and there you go, a lot of the orbiters, Juno, MRO, any of those like that, there's a lot of processing that goes into making those images into what you see here. So I'll zoom in here, and this I'll explain what we're looking at. So these are the actual individual framelets, the red, green, and blue framelets that make up the whole image itself. So the way our sensor works is we actually have four different filters on there: the red, green, and blue, and then actually a methane filter as well, the fourth methane filter. Each of those are 128 pixels tall, and as the spacecraft is spinning and the camera is pointed at the planet, it starts imaging in those 128 pixel tall framelets there, and then it just does that repeatedly throughout that spin, so that after that, I'll jump back really quick. After that, you get this whole spin throughout the whole planet of 128 pixel tall framelets that we're able to, like I said, use the time delayed integration before to remove all of the smear. And then from there, we're able to take those, stitch those together and make the nice seamless image that you see here. This image you see right here is this image back here. So again, since we know exactly where all those framelets are on our sensor, as well as we know exactly where the spacecraft itself was as it was going around the planet, we're able to nicely merge those together and make the seamless image, and then map all three red, green, and blue channels together to make the final color composite you see right here. So this one right here you're looking at, this is actually looking at the south pole of Jupiter. We're looking down kind of upwards at it. So this would be the equator, roughly the equator right about here, and then the South Pole itself. South Pole again looks kind of similar to the North Pole, where you got that kind of darker region, kind of circular region there, with again just really chaotic storms kind of all throughout the place. Again, storms rotating clockwise, some are counterclockwise, and then more that are just all over the place. So Again, very, very interesting way that we've got to that we have to image the planet, but it works very well, as you could see, and makes very, very, very pretty images in the end. And with that being said, what kind of talk would Jupiter be without, or what kind of Jupiter talk would it be without discussing the red spot? Everybody knows Jupiter's great red spot. It's definitely its defining characteristic. So a number of years ago, this was, I want to say 2016, 2017, or yeah, 2017 time frame, I believe, we actually had an opportunity. We were flying directly over top of the red spot, as in almost centered down the image. And there was no way we were going to miss that opportunity. So the next couple images here, I'll show you. This is the red spot itself. You could see we got relatively high detail in the end. Going a little further, this was the highest resolution image we were able to acquire of it. And the red spot itself is just so big, we actually can't fit it into the full field of view of the camera. You can see it's kind of scalloped here right there on the edges. That's just because the field of view of the camera was so narrow at that particular, or rather the red spot's so large and just didn't fit within the field of view of the camera at that particular spot. So very, very large storm in the end. And again, very chaotic, kind of just like the poles. You know, you can see this one spinning counterclockwise right there. But then inside there, you could see there's all sorts of different cloud bands kind of rotating in there. There's the darker spot in the middle. And then on top of that, you've got even more spinning clouds right here, somewhere right there. Kind of wisps of clouds going in all sorts of different directions as the entire thing is rotating there. So very interesting storm. You know, it's basically a gigantic hurricane on Jupiter. And really interesting thing to make note about the red spot that not everybody knows about. It's actually shrinking right now. So when I was a kid back in the early 90s, we would always say that you could fit 3 Earths side by side inside the red spot. It was that large. It's actually, believe it or not, down to only about 2 Earths will fit side by side within the red spot now. It's shrinking. We don't know exactly why. We don't know if it's going to continue to shrink. We don't know if it's going to disappear. We don't know if it might eventually just stagnate. Hopefully it doesn't go away. It is definitely Jupiter's defining characteristic there, certainly. But we'll certainly, you know, image it whenever we get an opportunity to fly over top of it. It is kind of interesting. I'll jump back to this other image right here really quickly. It is pretty interesting. If you look at some of the Hubble images of Jupiter from definitely throughout the 90s, you'll notice those images, the red spot is much more elliptical, whereas now it's definitely gotten much more of a circle shape there. So it's definitely shrinking in there from the outside. So pretty interesting. I'm admittedly not an atmospheric scientist, so I really couldn't tell you anything exactly why that may or may not be happening. But pretty interesting nonetheless. So we'll certainly, like I said, image it, you know, any chance we get, especially if we're directly over top. We will definitely continue to get images of that, really just to monitor it and see, you know, how much has it shrunk even from when we first imaged this a number of years ago. So with that being said, the Jupiter imaging is awesome. Absolutely. But with the extended mission, one of the greatest things we're able to do, I think, is we're able to change up our orbit ever so slightly. And that's allowed us to finally be able to see some of the Galilean satellites really up close. So just a couple months ago, we had a close flyby of Ganymede. And this is one of the number images that we took. Again, you know, it's kind of so big, we couldn't even get in the field of view of the camera. So we're kind of cut off right there on the side. But very beautiful image. This is pretty, I think, probably the highest resolution image we've really had of Ganymede. Lots of interesting terrain within the moon itself. I really don't know very much about it, but this image alone really has kind of spurred me on to really start figuring out, as a geologist, what exactly is going on here. So lots of impact craters, very interesting. Honestly, looks kind of like our moon with the large impactor on the bottom. Kind of hard to see in this image, but you can definitely see, I'll give you the URL to our webpage here in a little bit. And if you look at the full scale image, there's even a crater chain right there. I think I counted like 13 individual impact craters all right there. So very interesting moon, and actually the largest moon in our solar system. So really happy that we were able to do this just a couple months ago. And we're definitely going to continue for all the satellites that we end up getting close flybys with. We're definitely going to image all of them. So that being said, here are the URLs for both MSL and Juno. Highly recommend you go. Both websites are updated regularly. MSL obviously more often because with Juno, like I said, we're in that elliptical orbit, so we only plan it once every. We only plan images once every month and a half. But the images for MSL, when they come down, they show up on the website within about 24 hours. And then with Juno, same thing. When we do have our orbit and we start sending the data back, takes a couple more days. As I was saying, with the processing we have to do, in addition to knowing, our camera, we also need to know exactly where the spacecraft was. So it takes a couple of days to get all that telemetry down so they can be compiled into the data products we need in order to be able to process those images to make the really nice final products you see there. But so like I said, within a few days, usually we're able to get all that telemetry down and start updating those to the website. And the really fun thing with the Juno website is, since we're like I said, we made this more of a public outreach camera, anyone can go to the website, you can make an account, you don't have to be a scientist or a professor at some big university, no sorts of affiliations like that. You just go to the website, make an account, and you could join in on the discussion of what we want to image next. Or even cooler yet, you could take our images, download them, have fun with them, color stretch them, do whatever you want, and then re-upload them to the website as yourself and be able to share them with the rest of the world. So definitely recommend you do that, really, for both sites. Lots of great data on both websites. So with that, that's my talk. I think we got some time here. Definitely open up the floor for any questions y'all have, and I'll answer them for you. So thank you.
Yeah, and you very, very much. We've got a crew here that really is fascinated by this sort of thing. I'd like to start with a question about the cameras on Mars.
Yeah.
I understand that the surface is very, very powdery, probably as fine a powder as maybe baking flour. Why aren't the lenses coated with dust? How do you keep that from happening? Because I know you don't have windshield wipers on those.
Yeah. So it's interesting to know with Molly that the images, or excuse me, with Marty, the descent imager, with those images I was showing you, that one actually is pretty heavily covered with dust. During EDL, their entry, descent, and landing, especially as we got close, the rocket engines were kicking up a lot of the dust, and it really kind of clouded up the lens there. Those images themselves, when you see the raw images, they're kind of cloudy, but fortunately, it's not bad enough. You could actually just do some color stretching and contrast stretching to make those look good. As far as the other two cameras, Molly and Mastcams, Molly itself does have a cover on it. So, we've got the camera head right there, and there's a cover that stays closed throughout the whole time. And we only open it up just when we're going to image rock. And once we're done with that, we will close the cover itself. And that's what keeps the dust off. And it's gotten pretty dusty throughout the years. We've done a number of images just to check where we kept the cover closed and just snapped an image like that. And it's extremely dusty on that lens itself. As far as the Mastcams go, there are no covers on that one. The way it works is kind of a couple little clever ways of doing things. For one, they are mounted up kind of high, and they are vertical, so it's a little harder for dust to kind of just collect up on there and pile on there with the lenses being vertical like that. The lenses really aren't exposed to the outside either. We do have a protective shield over that is clear. But then also one of the things we do at the end of the day with imaging is the mast itself. The head itself will actually kind of point downwards. So all the instruments will be pointed a bit down so that, again, you don't have a lot of dust building up, because any dust that does get on there is just going to be able to fall off pretty easily. So kind of a number of different ways, really, we're able to kind of mitigate the dust buildup with the Mastcams like that.
Other questions?
Hey, Daniel, you mentioned the challenges for the Juno spacecraft as it rotates to take pictures. Why is it rotating?
So it's really for stability for the spacecraft, because, like I said, we're in that highly elliptical orbit around the planet. It's the exact same, the physics are the exact same as like when you throw a football, you have a spin on the football, and that just makes it, gives it that much more stability. So that's really the idea behind it. When we actually very first got to Jupiter, the spacecraft, we're at a 2 RPM spin right now, but when we very first entered JOI, Jupiter Orbital Insertion, we actually got it up to about 5 RPMs because we were coming in really fast. We were actually one of the fastest spacecraft ever created in human space flight. So we came in screaming hot. We had to go at 5 RPMs, and then we, did a burn to help slow ourselves down. And just that stability was there, just so the spacecraft didn't start wobbling and kind of get out of sorts like that. So it's really all about physics.
We have a question from the chat here. How large in miles or kilometers is the red spot?
That's a good question. So let's see, if it's 2 Earths right now, I got to do some math in my head. I actually don't know the number off the top of my head. I think Earth's radius, what are you like? Is it 6,000 kilometers for Earth's radius? Yeah, I don't know off the top of my head, actually. That's a good one. I want to say Earth is, gosh, I think Earth is about 6,000 some odd kilometers in diameter, or maybe that's radius. I cannot remember. Yeah. I honestly do not know that one off the top of my head. That's
I think the Earth is about 4,000 miles in diameter. Or is that radius?
7,926.
There you go.
Okay, 7,000. Okay, yeah. So I guess, yeah, you could double that and you'd get a pretty good, yeah. So that's 15,000. Was that kilometers there, I'm thinking?
No, that's miles.
Oh, that's miles. Okay. Yeah. So yeah, basically double that. And that would give you a pretty rough estimate of what the red spot is. It's large.
Wind velocity is the clouds that are spinning through the red spot.
I don't know the velocity. I think some of the atmospheric scientists were doing stuff with that when we flew over top. Yeah, I don't know the number off the top of my head on that one. It's fast. I remember when we flew over top, you could even see just the handful of images we took, and then those were only spaced a couple minutes apart. You could actually even see movement going in there. So you figure if that thing is, 15, 16, 1,000 miles across there, and you could see that much movement in just a few minutes, that's got to be going thousands of miles an hour easily, would be my guess. Again, I'm not an atmospheric scientist, so certainly don't quote me on that one.
So in the images that you had there, especially like of Ganymede, you talked about planetary volcanology. So did you do anything with cryovolcanology?
I didn't do anything directly with cryovolcanology, or studied a little bit, certainly during when I was getting my degree. But yeah, I know like Enceladus, for example, at Saturn, it was really interesting with that. The physics are very similar between the two. It's just, one's spewing out magma, the other's spewing out, a different material. So yeah, I never really did anything myself directly with cryovolcanology.
How many people do you have working on like the planning for images, like say Juno, because you have it every, month and a half, 2 months or whatever?
Yeah.
How many people are working with you to plan those imaging sessions?
Yeah, so with Juno, we're actually a pretty small team. There's only like for the operations personnel, there's myself and 2 other people, as well as our PI, the principal investigator. So we're pretty small with that. So now, as I was mentioning, the camera itself is more of the public outreach camera. So there is a lot of discussion going on that website. So really, I mean, a lot of people, you could just join in on the website and kind of join in the discussion yourself. So we could really have, the core of us, doing the planning, but then the general public is really kind of giving inputs about, hey, it'd be really interesting if we did this or that. Certainly for MSL, we're a much larger mission, and the science team members, we've got, gosh, there's probably, I'd say at least 100 or so people working on that, science team members, let alone the operations personnel. So small for Juno, large for MSL.
Any shadow transits in your images from Jupiter?
Yeah, so we've got, there's a really good one. Oh, I really wish I put it in there now. I think it was the Io shadow went over top as we were going in there, and it's just clear, just this solid black spot right on Jupiter itself. Yeah, I wish I would have included that one now. Really cool. I mean, we didn't really expect it. You could figure out when you would have a shadow transit like that, just based on the orbit of all the planets. That's typically not something we do, just because really it's not something we're really looking out for, and it's just one of those things that if it happens and we get, that's really awesome. So
another.
Go
ahead. Yep, Tom, go ahead.
I was just going to ask if those were CCD or if they're CMOS type camera systems.
Yeah, so ours are CCDs. And one of the questions a lot of people ask is, CCDs certainly being a slightly older technology. A lot of people say, why are you using CCD versus CMOS or anything else? And really, it boils down to space cameras. You really got to make sure stuff is radiation hardened and could withstand the cold and all sorts of different, just a harsh environment, let alone the vibrations of launch. So the CCDs we use are all of that. They're tested, kind of tried and true elements themselves. So it's really, you use what you know is going to work. It's not that we only stick with old technology. Certainly, we're always experimenting with new things. But yeah, with a lot of the space technology you're going to see like that, it's very impressive for what it is, but consumer technology is like your cell phone would definitely have a higher resolution or higher quality image. But you couldn't put your cell phone on the surface of Mars and expect it to last very long at all. So we really use the older technology because we know it's tested, tried and true, and meant specifically for this environment.
Another chat question, are there any winds on Mars to account for with the camera? And my editorializing would be, they have sandstorms. Do you know they're coming?
Yeah, so like we did have the big global dust storm a number of years ago. Was that 2018, I think? Yeah, so we have seen dust like that kicking up. Certainly, actually, it was kind of interesting. All our images throughout that whole time, all the images were very orangey. It was pretty kind of surreal actually getting to see that. And we've seen even in addition just to winds and whatnot, we could see we'll see clouds in the atmosphere every now and then. You could actually see them moving. We had a really interesting video we did earlier on in the mission, and you could actually see the clouds themselves moving as they're going over top like that. So the wind, yeah, it's one of those things on Mars where it can kick up, certainly. It's not something we really have to take too much into consideration during a typical planning day. It's not like, oh, it's too windy, we can't, get the arm out or anything like that. But we also do take into consideration as the arm goes out, we do wait for it to kind of settle from bouncing down. And there have been times certainly where we took an image and came out a little blurrier than we expected. And we thought, oh, is something wrong with the camera? And reviewing the telemetry is like, nothing's wrong with the camera. It's like, oh, maybe at that moment right there as we were taking an image, just a gust of wind came by and kind of, jarred the cameras just a little bit there. So it is something that does happen, but not enough really to cause concern on a daily basis for us.
Do you relay those images from the up to the satellite and then relay them back to Earth? So there's that time delay there, or
yeah, they're definitely exactly. Yeah. So that's the main way we communicate, like getting our data back from the rover to Earth. We do have the ability to talk directly to Earth with the rover if we ever need it, but it does use a lot of power and it's obviously very slow to do so. So yeah, right now we relay with a number of satellites, 4 different satellites. There's Mars Reconnaissance Orbiter, Mars Odyssey. There's the Trace Gas Orbiter, which is an ESA, European Space Agency satellite. And then there's also the MAVEN spacecraft. So all 4 of those they'll be flying overhead at any given time, and we have dedicated time with them where the orbiter will communicate with the rover, and the rover will send the data up to the orbiter, and then the orbiter, which is meant to be communicating directly with Earth, that'll send it to Earth on what's called the DSN, the Deep Space Network, and then we get the data from there. So there definitely are delays. We don't do anything real time with the rover itself. It's all could be 6-hour delay maybe from getting the data depending on where the orbiters are, as well as when the orbiter could communicate even with the Deep Space Network itself.
Do you have stabilizers on those cameras?
For what we're doing, no, because it's kind of the same question with the wind there. There's not really much that we have to worry about with like vibrations or anything like that. So there's nothing we really need to take into consideration, like image stabilization wise, as we acquire an image.
Got another chat question. I think it's twofold. How long does it take to get from Earth to Jupiter? Might be referring to how long did the Juno spacecraft take? And then the other one you and I talked about earlier, how long does it take to talk to it and get an answer back?
Yeah, so well, as far to answer the first part, then yeah, definitely. It took a long time to get from Earth to Jupiter. So we launched in, I believe, it was August of 2011. Before I even hired in, I was still in the interview process at that point. Launched in 2011. We did not get to Jupiter until July 4th, believe it or not, of 2016. So it was about 5 years just to get from Earth to Jupiter. And then yeah, as far as getting a signal from Earth to Jupiter or vice versa. It does depend on the orbit of the planets, how close they are, how far away they are. As we were talking earlier, yeah, right now we're at about 33 minutes to get a signal from Earth to Jupiter. That's called the one-way light time. I think the largest delay that is just a little under an hour, 50 some odd minutes. Kind of put that in perspective, Jupiter being that far away, it's kind of interesting to know that it only takes, at worst case scenario, a little less than an hour to be able to get a signal from Earth to Jupiter like that. Mars itself is, I think, worst case scenario is about 15 minutes to get the signal from Earth to Mars.
Early on, just after landing, of course, everybody can tell that Mars is pretty much monochromatic, but like that meteor, something once in a while stands out that's brightly colored. There was a considerable amount of publicity about a bright green, sea green rock, and the news media said it was analyzed, but we never heard what that was. Can you say anything about that one?
I'm trying to think which one that might have been. Yeah, and I actually don't remember off the top of my head which one that was. Was that Jake M? I can't remember the name of that rock. If it's the one I'm thinking of, yeah, I don't think that was it. I honestly I can't answer that only because I'm not entirely sure which one that was. So I don't want to give an incorrect answer on that one. Yeah, I will say the environment that we're in for Curiosity inside the crater kind of surprised us when we did our first drill. I myself definitely expected it to be kind of red dust that came out and ended up being gray. Turned out we were in a very clay-rich environment, and that was one of the things we were trying to decide. Was water once flowing in this area, and that's ultimately what came to be. So. Yeah, instead of being, the red planet, we kind of turned it into the gray planet we kind of joked about because it was all clay in there. So yeah, that was pretty interesting. So yeah, as far as the greenish colored rock, I don't know exactly which one you might be referring to on that. So I don't want to answer that just because I don't want to accidentally get the wrong answer.
You mentioned cell cameras. I recently discovered the nighttime feature on my cell camera, and it's amazing how much you can pick up in dim light. Mars and especially Jupiter, the lighting is not at all like it is here on Earth. How do you make those cameras that much more sensitive to low light?
So with Mars, I'd mentioned we could do the lower light imaging. Really, we've done some mass cam imaging of like the stars. We had a comet fly overhead at one point, and we tried to image that. In the end, that camera really wasn't designed for that. So it really didn't come out very well at all. There's a lot of noise on the sensor itself. We would have had to spend a lot more time really to tweak the sensor and tune it down so we'd be able to, do just a long exposure is really what we would have to do, but then be able to remove the noise. As far as Jupiter goes, that really kind of comes into play with the TDI. Like I said, the time delayed integration. We do have the ability to set the exposure on it as well. So really that's kind of what it boils down to. It's just kind of clever software work there just to say, okay, with the TDI and the default exposure will be, X amount of milliseconds. That's really just kind of how it has to be done. I can't give you too straightforward an answer on that just because I didn't design the Juno camera. I'm just doing the operations on that. So, but yeah, that is what we do typically for planning is just make sure we got the right TDI set and make sure the exposure is high enough so that we're able to pick up, like you said, some of the much lower light environment like that.
Another question here.
What's the expected lifetime of the mission on the Mars rover?
So the expected lifetime the mission itself was planned to be 2 years. We are actually now in our 9th year as of quite literally just a couple weeks ago. So that's one of those things where it's going to keep going if we've got funding and the instrumentation's working. keep using it. You know, it's a very viable spacecraft that's returning great science. So yeah, so it's 2 years was the expected, but here we are. You know, in the Spirit and Opportunity, kind of the same thing. You know, Opportunity that went 14 years almost. So yeah, the spacecraft themselves are engineered very well, kind of. You know, very well, where they're going to be able to withstand quite a bit. So as long as there's funding, really, that's the life expectancy, in my opinion.
Here's a good one that I don't know if it's a final question or not, but it's a good final question. What future projects are you working on?
So yeah, so really, right now for me, I'm focused mostly on Juno and MSL. I did do a little bit of work on the Perseverance rover, because like I said, we got a couple cameras on that. I eventually went back to MSL just because I was needed on that one specifically. So at some point, yeah, might be some more stuff with 2020. That's kind of those things where just only time will tell. As well as, you know, as a company that builds cameras like that, we're really, you know, dependent on, you know, getting contracts. So every time the government puts out, you know, they say, oh, we're making a spacecraft that's going to go to such and such location, and it needs to have this payload on it, one of which happens to be a camera. We'll certainly write a proposal and say, okay, we could build the camera that fits those specifications and does all this, and then from there, you know, NASA decides, you know, whether they give us the contract or someone else. So that one's just only time will tell. We'll certainly see. So
Any others? Daniel, thank you very, very much for being here with us tonight. We really appreciate it. One of the things that we always express to our speakers is our appreciation by making a contribution in your honor and in your name to our scholarship fund for second-year college students who have made a serious commitment to studying space science at the advanced level. So you will be one of the folks that helps us meet our commitment and our mission to education. So we thank you for that very much. And along those lines, I'd like to announce next month's speaker. A lot of us here know him very well, Darren Williams. Darren started here as a young person interested in astronomy and has now gone all the way through his PhD and become an astrophysicist teaching at Penn State Barron. And one of his special interests is planetary atmospheres, and especially talking about exoplanets. So if you'd like to know what sunrise and sunset are on a planet 20 or 30 light years from here, Darren might have something to say about that. So that's for next month. But in the meantime, Daniel, once again, thank you very much for being part of this. You've really helped us with our mission, and it's been a fascinating time to spend with you. Thank you.
yeah, well, thank you all very much for having me. I'm
Thanks, Daniel.
very happy to be here. This was a lot of fun. Y'all had very good questions too.
Great. It's good stuff. Thank you.